Hey guys, welcome back for another chemistry lesson. In this video, we're going to talk about quantum numbers and how they are related to orbital shapes. So, quantum numbers, before I discuss what's on this slide, quantum numbers are numbers and or letters actually that describe specific it's almost like a seating chart for the atom, for the electrons in the atom, so you know exactly where an electron is and what it's doing with any given number. So, the first one we're going to talk about is the principal quantum number, which is n. And the principal quantum number characterizes the energy of an electron in a particular orbital. So these are the energy levels in the Bohr model of the atom. So n can be any integer greater than or equal to 1. So n equals 1, n equals 2, n equals 3, etc. And the larger the value of n, the more energy the orbital has. And our energies are defined as being negative. And so it would have 0 energy when it escapes the atom, and then more and more negative along the way. So the larger the value of n, the larger the orbital, and as n gets larger, the amount of energy between the orbitals gets smaller. So here we can see there's an equation that kind of summarizes that. And the energy in whatever energy level we're talking about, so n, is equal to negative 2.18 times 10 to the negative 18th joules times 1 over n squared. So second energy level, that would be 2 squared. Fourth energy level, that'd be 4 squared, etc. So you don't have to do this math. The math has already been done. So here are the energies for the energy levels in hydrogen. The next quantum number we're going to talk about is the angular momentum quantum number, which we represent with an L, a lowercase l. And the angular momentum quantum number determines the shape of the orbital. So this number can have integer values from 0 to whatever n is minus 1. So if n was 5, they would be numbers from 0 to 4, right? Because n minus 1, right? So each value of L is called a particular letter that designates the shape of the orbital. We have s orbitals that are spherical, p orbitals that are kind of like two balloons that are tied together at the knot to make like that kind of shape, right? D orbitals are like 4 balloons that are tied at the knots, kind of. And f orbitals are like 8 balloons that are tied together at the knots. It is much more complicated than that, but that's the general shape of most of those orbitals. Okay, so really quickly, atomic spectroscopy is each wavelength of the spectrum of an atom corresponds to an electron transition between orbitals. So when an electron is excited, it transitions from lower energy to higher energy. And then when it relaxes, it transitions from higher energy to lower energy. Hopefully that makes sense. So when an electron relaxes, a photon of light is released. And that energy equals the difference between the orbitals. I'm going to add right up there a card to the emission spectra video that I have discussed that in. So let's talk about those electron transitions. In order to transition to a higher state, the electron has to gain the right amount of energy that corresponds to the difference between where it starts and where it ends, right? Electrons in high energy states are really unstable, so they're going to lose that energy and end up back at the lower energy level. And so each line in the emission spectrum, which I referred to that video previously, I put a little card up there, but I'll put it in the description. But each line in that emission spectrum corresponds to the difference between those energy levels, right? And this is where the idea of quantum leaps come from. So we've got an electron here, it gets excited. That's unstable, so it drops down and becomes a little more stable and emits light as it does so. So the energy of a photon that is released is equal to that difference in energy from where it drops down, right? So we can calculate that by subtracting the energy of the initial state from the energy of the final state. So there is a formula. It looks really complicated, but if you think about it just like this is where it started, however far out, and then it dropped down to this is where it ended. And so this is a kind of calculation that you need to be comfortable with. And the energy of the photon that it releases is equal to the speed of light over the wavelength of the light times Planck's constant. So because of this equality here, we can calculate the wavelength of the light and figure out what color it's going to be, if it's going to even be visible, based on how much energy the photon has. And now we know we can plug it into this equation. So for hydrogen, in the emission spectrum video, I showed you the 3 colors that hydrogen emits. Well, that wasn't fully right. It's just the 3 colors that we can see that hydrogen emits, which are purple and then like a blue-green and then red. Hydrogen also emits infrared wavelengths and UV wavelengths. Those are just not visible to us, right? So this is what we can see. That's the important piece that will help us identify elements if we're doing this in a lab with like flame tests. All right, so really quickly, we have this probability and radial distribution function that we could talk about. This is really more of a quantum physics type topic, but I need to bring it up because this is related to the orbital shapes that we are going to talk about. So this is how we indicate our probability density, and what that tells us, this is from Schrodinger's equation, what that tells us is the probability of finding an electron at a specific point. So the probability of finding it here, for example. For s orbitals, the maximum is at the nucleus, and it decreases as you get further away from the nucleus. So we typically represent that visually as a fuzzy cloud that's darker in the center and gets lighter towards the edge. So this distribution function, the radial distribution function, represents the total probability at a certain distance from the nucleus. And the maximum of that is at the most probable radius. And so you can see here nodes are the functions where the probability drops to 0. We're not going to find stuff here, right? So the probability density for our s orbitals, so that would be L equals 0 for our angular momentum, is related to this spherical shape, right? So the probability function represents the total probability of finding an electron at a particular point in space. Our maximum is here, and we decrease as we get further out. And so you can see a graphical representation here. So we look at s orbitals being spherical. They are the lowest in energy of our orbitals, and they have n minus 0 nodes, right? There's nowhere in that we're not going to find them, okay? Right? Our probability densities for 3s and 2s orbitals, we do have some areas where we're not going to find them there. And you can see that in this diagram. But the important piece for you to know for the purpose of this general chemistry class is that our s orbitals are spherical. Our next angular momentum value is L equals 1, and that is for our p orbitals. So for every energy level above n equals 1, we've got 3 p orbitals. We think of it just as p orbital, but it's really 3 different p orbitals at different angles. So p sub x in the x direction, think about a graph, p sub y, and then p sub z coming like towards and away from you. This is the second lowest energy orbitals in our principal energy state. So n equals 2, I have an s orbital and then the p orbitals, and s is lower than p. They are 2-lobed and kind of look like balloons. I'll show you in a minute. And they have 1 node at the nucleus for a total of n nodes. So if n equals 1, then we have 1 node. N equals 2, we have 2 nodes, etc. All right, so here we can see you've got your x, and notice here we don't have it drawn in the middle. It looks kind of like balloons tied together, but not quite, because of that space in the middle. So we have p sub x, p sub y, and p sub z. The next kind of orbital is our d orbital. Each principal energy level above n equals 2 has 5 d orbitals. So for n equals 3, we have 5 d orbitals, right? And they are aligned in different planes, like the p orbitals, but there are not 5 different planes, so it's a little more complicated than that. And there's a picture on the next slide. But they are the 3rd lowest in energy level, so in any principal energy level, n equals 3, n equals 4, n equals 5, it's always S, P, D in that order. They are mainly 4-lobed, but they do have one that's 2-lobed with a toroid, which is like a donut. So this is the shapes. We have 4, 4, 4, 4. This one's, I don't know, it's not super clear, but this is rotated 90 degrees from this. So same plane, just rotated 90 degrees. And then this is our toroid in the middle. And then our final orbital shape is our f orbitals. Each energy level, principal energy level above n equals 3, has 7 f orbitals. This is the 4th lowest energy level, so it's the highest energy level in any energy level. So in n equals 4, we have s orbitals, p orbitals, d orbitals, and then f orbitals. It always goes in that order within a principal energy level. They are 8-lobed. It looks insane. I've got a picture on the next slide. But we do also have some 2-lobed ones with the toroid in the middle. So like I said, it looks totally insane. Here's our 8 lobes. 8 lobes rotated, 8 rotated. And then these are the ones with the little donuts on them. So all of this makes up the f orbitals within a principal energy level. And so when we have all of the beautiful, ridiculous-looking orbitals overlapping, this is what makes an atom spherical. It's that overlap of shapes.